If you like this video, be sure to check out our Skool community, U of T Eng Math, where we have weekly review sessions. You can ask questions and get answers. There's lots of videos, of course, as well. And we do exam, midterm, and final exam review, and you can check it out here. There's also a link in the description. Also, don't forget to like and subscribe. Okay, so in the last video, we looked at the arcsine function, the inverse of the sine function, the function that takes the output of sine and sends it back to the input that it came from. And we saw how we have to restrict the domain of the sine function so that we can have this inverse relationship, right? So that we can have arcsine of sine is equal to x, but also explain why, this is what started the whole thing off, why arcsine of sine of 3 pi over 2 is actually equal to negative pi over 2 and not 3 pi over 2. And why that makes sense, right? Why that makes sense. And this can be true at the same time. It's because x is actually in this restricted interval, right? With x in the domain negative pi over 2 to pi over 2, then this is true. But we never really, so what we're going to do in this is we're going to graph it, right? We said at the end that we should learn how to graph it, and this is one of the trickier things that you do in university math, in Eng math, and a lot of math programs. You have to do this, and it kind of bends your brain sort of onto the side. I remember how confusing this was when I did it for the first time a very long time ago. But we're going to see how to make it not so confusing. We're going to non-confuse it, but we're going to address why this what is we didn't talk about the full significance of this, right? Because it seems like this shouldn't be possible, right? It seems like I just said x has to be in negative pi over 2 to pi over 2, and then sine or arcsine of sine of x is going to be equal to x, but then we put this 3 pi over 2 into sine, right? And then said arcsine of sine of that. So this would be like the x. That's negative pi over 2, which is a different x, right? So it still seems like something is off here. And this is actually important, especially for engineers, for anyone doing applied stuff. What's actually going on here, right, is that what goes in, sine of 3 pi over 2, right, sine of 3 pi over 2 is negative 1, right? We can see that from, actually, I erased the graph, but hopefully we can check the unit circle and know that sine of 3 pi over 2 is negative 1. So this is actually saying, this equation is actually saying that arcsine of negative 1 is negative pi over 2, right? We saw that actually there are infinitely many x's that sine sends to negative 1, right? There was negative pi over 2. There was also 3 pi over 2, right? Infinitely many that get sent there. And the idea is that arcsine can't tell the difference between them. The sine inverse function, and this is the important thing for you. This includes, for engineers, for applied people, includes calculators. When you do a sine inverse on a calculator, if you plug sine inverse of negative 1 into a calculator, it's going to give you negative pi over 2, or actually a decimal approximation of that, right? This actually comes up when you're trying to solve for angles, when you're using the ambiguous case of the sine law. So you could be trying to solve for a triangle where the angle that you're trying to find is an obtuse angle, right? Is bigger than 90. You can get a situation like that. But the sine inverse, because it only outputs values in negative pi over 2 to pi over 2, right? It will give you an acute angle that has the same sine value. And that's what ambiguous triangles are about. It seems like this weird pathological high school thing, but it's actually really important to know this because you could be getting the wrong angle, right? Your angle could be, so the answer that you get could be this, if it's in degrees, it could give you an angle of 30, but the angle in the triangle is actually 150, right? There are other videos where we go into this in depth, but the point I'm trying to make with this is that the arcsine function can't see that this is sine of 3 pi over 2. It sees that it is negative 1, right? Or if it was 1, it wouldn't see that it was sine of pi over 2, right? Or that it was sine of pi over 2 plus 2 pi, some integer multiple of 2 pi, right? It just sees the number and it picks one value in this range to send it to, and it sends it to that one, right? So we actually really do need to be aware of this, or we can have bad mistakes that come out. And it's not just losing marks, right? For you guys, it could be, bridges collapsing, planes falling out of the sky, whatever it is, right? There's a whole new significance to being able to validate and verify your answers, and this is one of the sort of sneaky ones. So this stuff actually really, really matters. Okay, that being said, let's graph this thing. So I'm going to get rid of this stuff. I'm going to get rid of these things in here, and we're going to keep our sine function, our restricted sine function, which is going from negative pi over 2 to negative 1, 1 here. Here we can see this is the interval from negative pi over 2, and it goes up to 1 at the top here. That's its max, and then it goes down to negative 1. That's its min. So arcsine, its domain, right, is the range, the also the codomain of the function, right? The domain of the inverse is the codomain, the range, which and if you're wondering why I'm using this word, another video in which we talk about codomains and ranges and all the subtleties about that. For now, don't worry about it. You can just think about this as the range. We restrict the codomain to be the same as the range is what's going on. But don't worry about that for now. The range of sine is the domain of sine inverse, and the range of sine inverse is the domain of sine, right? Vice versa, right? They create these one-to-one mappings or correspondences, which we talk about in other videos. So it takes in its domain is going to be negative 1 to 1. So I'm going to try to put here on the same scale. I made the one kind of one of these blocks and a half, and then the pi over 2 kind of two of them, right? So because pi over 2 is bigger than 1. So I'm going to do the same thing. I'm going to come down here and I'll put in 1 here and negative 1 here, trying to maintain that same scale, right? And then up here, I'm going to put pi over 2, and down here, negative pi over 2. So these are the marks we're kind of aiming at, because you might be thinking, I remember how much this turned my brain on its side when I did this a long time ago. It just kind of hurts to try to do it. But like so many things in math, you do it enough and you think about it enough and you stare at it enough and you come up with a process for it and it becomes actually very, very doable. So, but we're going to do, and actually cosine is harder. We'll do cosine inverse next. This one, we have sine inverse here. What are the points on this graph? We have negative pi over 2 and negative 1, and we have pi over 2 and 1. When we invert a function, and again, this is explained in more depth in the sort of concept videos on this, on invertibility in general. Here we're doing a specific example of this, which is the inverse sine, paying attention to that. We do this in a lot more depth and generality in the other videos. We see why this is equivalent to flipping it geometrically, the graphical picture, as we say, is equivalent to flipping it across the line, y is equal to x. This is equivalent to switching the x and y coordinates, which is actually the same thing as sending everything back where it came from, which is the way that we looked at it in this video. So if pi over 2, 1 is on the graph of the original function, then on its inverse is going to be the point, and let's pick a different color for this to make it sort of stand out a bit, is going to be the point 1 pi over 2, right? If x, y is in the graph of f, then this is actually an if and only if, y, x is in the graph of f inverse. And this elementhood notation, if you haven't seen this, if you're wondering what this means to be in a function, technically functions are sets of ordered pairs. This is all gone into in a lot of detail in other videos. For now, we're just thinking if x, y, so this is the x, this is the y, it's on the graph of the function, sine function, then the inverse is going to have yx. It's going to be 1 pi over 2. Same thing here. Pi, and this, by the way, this little line that I've drawn, this is showing us that this is the equivalent of reflecting this point across the line, y is equal to x. And what does reflecting mean? It means we start here, we come straight at a right angle. That's what these little marks here mean, right? Those little sort of angles there. That's a right angle, of course. We come at a right angle, and then we go across the same amount. That's what those little tick marks here are meant to mean, that these distances are the same. Of course, I'm drawing this by hand, so it's not perfect, but the idea is to reflect across a line, we go at a right angle to the line, and we go the same distance past there, and then we stop, right? This would be x, y. This would be y, x. And by the way, if you're thinking, doesn't the x coordinate come first? This is for a particular x point here, right? Here, pi over 2 is the x. So the x value here is pi over 2. That means the y value here, the y coordinate there is pi over 2. Here the y was 1. Here the x is 1. Okay, and so then we do the same thing with negative pi over 2, negative 1, right? We get this point here, which is negative. So we, again, flip it across the line y is equal to x. And we get this point, which is negative 1, negative pi over 2. And here, right here is pi over 2 there on the y-axis. There is negative 1 on the x-axis. And so we have these 2 points to kind of guide us. Now comes the sort of leap of faith, mind-bending sort of weirdness where we're going to connect them in a way that looks like we've reflected all the other points across. And it's going to look like this, like that. And the scale is a little bit off if you Desmos this or if you get some other app to make it perfectly accurate. It's going to look a little bit different from this, right? Because of the scale is so imprecise. But this is the relationship between them, right? They only ever cross on the line y is equal to x. Every function only ever crosses its inverse on the line y is equal to x, and it is the reflection of the inverse in y is equal the line y is equal to x. And again, if you have a point, let me draw this in here. X0, Y0, and I'll put the subscripts on to let you know that to show that these are fixed points, right? Those are actual numbers, not variables. If x0, y0 is on the graph of the function, then y0, x0 is on the graph of the inverse, like this. So we reflect it again across there. And this one is even more less to scale because again, I'm doing everything by hand, but hopefully we get the idea with this. And so bits of advice on how to graph this because I remember how much I struggled with this, how much everyone struggles with this. It's weird to think about it now. It feels so natural to me doing it now. The first time I tried it, I thought my brain was going to fall out my ear, right? It feels really, really weird doing it. It's even worse with Arccos. We'll do that next. But this is why it's important to be consistent with these courses and do and practice every day and work on them every day and stare at them and think about them constantly because it takes time for the neural nets or whatever it is to grow in your brain. I'm pretty sure it's neural nets. It takes time for those things to grow in your brain. It takes time for these things to work their way in and for your brain to become saturated with them, right? It's not like other courses where you can cram the night before. I never advise doing that, by the way. I took some bird courses during my degree, some humanities courses where I just crammed the night before and got an A and it was right. Math is not like that. We have to work every day. It's like training a muscle, right? It's like you can't start working out the night before your weightlifting competition or something. It takes weeks or months or I don't know how long. I'm not a bodybuilder, but the point is you have to be doing this consistently. You have to if you have trouble with graphing the sine function, do it 10 times, right? Keep doing it, keep graphing, keep staring at it, keep thinking about it. Do it every day until it works its way into your brain. Whatever it is, the concept that you can't understand, you just keep at it and keep at it and keep at it and stare at it and think about it and do it again and again and again. And eventually this is how you make stuff easy, right? This is how you take stuff from being this deep conceptual stuff and this saturation and this repetition and this. And don't mindlessly repeat it, by the way. All the evidence shows, and this is true, and also from experience, that you have to be concentrating on. It. You have to be thinking about it. You have to be trying to understand. You can't just write it out a million times. But eventually it goes from, and this is the experience of math majors, which of course I was one. Something which seems impossible, seems like you're never going to understand it. You do it enough, you think about it enough, you struggle with it enough, and then the next thing you know, it's just the easiest thing in the world, right? And it's that neural net has grown in your brain, like riding a bicycle where you fall off and fall off and fall off when you're a kid, and then eventually you can do it and you never think about it again, right? Your brain grew the part of it that does this. And that's how you get it to go from feeling weird and awkward and impossible to just being second nature. So I always like to mention this to early in the videos, the topics I know people are going to be doing fairly early in the course, because so many people give up. So many people get disheartened and give up. They think this feels impossible. I can't do this, right? They have that kind of same feeling when you're a kid of falling off the bicycle. Feels like you just can't do it. But if you keep at it, again, I promise you will be able to do it eventually. You just have to try. You have to keep at it. And also, you can do things, cool stuff like this, like going to our Skool community and seeing all the videos that we have there, and asking questions, and going to the office hours, and the weekly review sessions, and the term test review, and also final exam review that we have, the live Q&A. And also we do tons and tons of questions, tons and tons of worked examples, and answer questions, and have lots of time for that. And they're actually very long because we get as much in as we can. And we do a lot of different time slots so that everyone can make them, right? If you're worried, oh, I won't be able to make it, it'll just be one day once, we don't do it, right? We do multiple for every exam, and we book lots of time for it. So all of that cool stuff is there. And also, don't forget to like and subscribe, I think I'm supposed to say as well. I will see you in the next video, which is going to be graphing discovering again the inverse cosine function, which is really, really exciting. What is its domain going to be? I don't know. We're going to discover this as we go, figure it out, and then we're going to graph the thing. So I'll see you in the next video.